Hey, good morning, everybody. This is Mr. Aynesworth here, and we're going to be getting into our second lesson here in Unit 7 in AP Pre-Calc. And we're going to be talking about the inverse functions, okay, and how to find the angle when you're given a ratio, basically. And then we also want to learn, how does that happen? There's some restrictions involved, so let's get right into it and discover what we need to do to find the inverse of a ratio when we need to solve an equation, because that's where we're headed. So let's do a little reading here. We have seen how we can use a unit circle, on the graphs of trig functions to evaluate sine, cosine, tangent at various angles. Okay, that's nothing new. But what if we're given a ratio and we want to find the angle? What happens if we go backwards? Okay, so here we go. Let's start evaluating here. All right, so what is the sine of 7 pi 6? Okay, and you don't need the unit circle here, although if you want a unit circle, go grab one if you want, okay? But as I've told you guys many times in class, you don't need one. So I'm just gonna draw some special right triangles here. All right, I'm gonna draw the 30, 60, 90. So we got 30, 60, 90 right here, and the sides are 2, 1, rad 3, okay? You can get all these ratios just by looking at these two little triangles here, the 45, 45, 90. Okay, it's isosceles, so the sides are 1 and the hypotenuse is rad 2. And if you just know some trig basics like sine is opposite over hypotenuse, cosine is adjacent divided by hypotenuse, and tangent is opposite divided by adjacent, you can figure out all of these things. And of course, you can memorize a unit circle. You can do that, okay, but it's really not necessary. Although some people say it is, I would disagree, because I don't use it. I know it, but I don't need it. Okay, so anyways, here we go. So sine of 7 pi 6, now 7 pi 6, or 7 6 pi, is 1 and 1 6 pi. And so if you guys know your radians, we got pi halves at the top, we got pi as a half revolution, and we got 3 halves pi at the bottom here, right back to 2 pi. All right, and so this is quadrant 1, quadrant 2, quadrant 3, quadrant 4, right here. If you know your quadrants, 1 and 1 6 pi is half a revolution plus a little bit more. So guess what? This puts you in quadrant 3. All right, and guess what? Sine's negative down there because the y coordinates are negative down there. So this is equivalent to negative sine of pi 6. That's your reference angle. The reference angle is always this little bit more here. Or you can find the reference angle by subtracting pi or 180. You could do that too. And then pi 6, well, guess what? That's 180 divided by 6, or 30 degrees. And the sine of 30 degrees is 1/2, so this is equal to negative 1/2. Okay? There we go. Okay, this one here, negative pi 6, that's a clockwise rotation. That's quadrant 4. Okay, that's quadrant 4, and that's equivalent, and sine's negative down there, so this is equivalent to negative sine of pi 6, and as I just said earlier here, that is negative 1/2. Okay, your 11 pi 6, if you know your fractions, that's 1 and 5/6 pi. That's almost 2 pi. That's quadrant 4 right there, guys. And your 1 pi, that's halfway around, plus 5/6 more, that puts you in quadrant 4. Sine's negative down there, and the reference angle is 2 pi minus that, or 12 pi 6 minus 11 pi 6, which is 1/6, but it's a negative number. And the reference angle is pi 6, and so you get negative 1/2 again. Look at this. We're getting negative 1/2 every single time. What's going on here? What is going on here? Okay, now 19 pi 6, what is that? Well, 19 divided by 6 is usually 3 and 1/6, right? Okay, Now, what's coterminal with that? Let's subtract 2 pi. Okay, and guess what? 3 minus 2 is 1, so this is 1 and 1/6 pi. And guess what? That's 7/6 pi, and we already did that. So this is equivalent to sine of 7/6 pi. All right, we already know that that's negative 1/2. So you got to evaluate your functions and know, you know your 30, 60, 90 and your 45, 45, 90. And of course, like I said, you can memorize the unit circle, and if you want to do that, that's fine. There's many different ways of doing things, and as long as you're thinking correctly, it's all good. Okay, number 2, plot the order pairs from the question above on the graph shown to the right. Okie dokie. Plot the order pairs from question 1. Let me see. Okay, so the order pair, it looks like here we have to plot, let me see, the input angle. The input here is theta, so we have to plot 7 6 pi, comma, negative 1/2. So 7 6 pi, that's 1/16 pi, comma, negative 1/2, so that's right here. Okay, so we got 7 6 pi here. It's obviously a little bit more than a pi, so it's got to be to the right. Down 1/2 because it's negative. Next point is negative 1/6 pi, so negative pi over 6, comma, negative 1/2. And you plot that, you got to go left now, okay, because it's negative, and then you got to go down 1/2, so right here. So this right here is negative pi 6, because it's a negative angle, it's got to be left of 0. And then the next one, 11 pi 6, comma, negative 1/2. It goes theta, comma, value. Okay, remember the first number is your angle, your theta, all right, and the output is your ratio, right? So let me see, that's 1/5/6 pi, that's almost 2 pi, so it's got to be right here. So 11 pi 6. And then the last one here, where's that? So let me see. So that's 3 1/6 pi. So 3 1/6 pi is greater than 3 pi, so it's got to be here. So this is 19 pi 6 right here, comma, negative 1/2. And notice this horizontal line right through here. Okay, that is y equals negative 1/2. Notice that. Okay, and so those are the order pairs. We plotted them. Okay, we're good there. Number 3, how many solutions are there to the equation? The sine of what angle gives you negative 1/2? Okay, so there, remember, theta here. Theta is an angle. So the sine of what angles gives you a negative 1/2 ratio? Well, in the graph here, there's 4 shown. Okay, there are 4 in the graph, but actually if you take a look at their coterminal angles here and you continue the graph of sine, all right, remember this graph is infinite right here. The sine never stops. It waves, okay? It oscillates up and down forever, and this horizontal line at negative 1/2, well, guess what? That goes on forever too. So this would have an infinite number of solutions here. However, 4 is shown, so I'm going to respond this way. 4 is shown on the graph. 4 are shown on the graph, okay? But, okay, there are infinite many because we can add multiples of the period, which is 2 pi, and get their coterminal angles, which would give you the same values, okay? But coterminal angles here, found by adding 2 pi, which is the period. Okay, to each of these angles here, because if you add 2 pi to any of these angles, you're going to get a coterminal angle, which would give you the same value of negative 1/2. So 4 is shown on the graph, but coterminal angles found by adding 2 pi would also work. That implies that there's infinitely many, okay? So my end response here is that there's infinitely many solutions. Look at that, okay? And so, yeah, okay, these trig functions can have infinitely many solutions unless we restrict the domain or something. Okay, so the next question is interesting here. How would you evaluate sine inverse of negative 1/2? All right, which gives you an angle. The inverse sine takes you from the ratio back to the angle. Okay? So your theta is your input, your output is a ratio. If you take the inverse of the ratio, it should take you back to the angle. So this is equal to an angle. So the sine of the inverse sine, or what we say arc sine. So write down inverse sine. Actually, let me put this in red here because it's important. Okay, so this notation right here, okay, it's called the inverse. Okay, or there's an old terminology, they call it arcsine. Okay, arcsine or inverse sine. Customarily, I'm used to inverse sine. I very rarely say arcsine, but hey, you got to know both because guess what? In the context of this class, you may see both and you have to respond whenever you see arcsine and inverse sine, the same thing. Okay, so the inverse sine of your ratio, which is -1/2, is an angle, equals an angle right here. Okay, but what should it be equal to? Should it be equal to the -π6, 7π6, 11π6, 19π6? What should that be equal to? Like, we want the inverse function to return only one answer. So how can we make that happen? Because if this question had multiple answers and everybody got a different answer, we would have a problem here. Okay, we need the inverse function to return only one answer. So let me put that in red too as well. So we need the inverse function, okay, which is arcsine in this case. The inverse function all right, to return only one angle. When I say return, I'm talking about give us. To return only one angle or solution, okay? We don't want to have multiple solutions to a problem because that would cause some problems in real life applications. All right, so how do we do that? Well, number 4 leads us in that direction. So let's take a look at what number 4 says. Okay, it says y equals sine theta, or is y equals sine theta, which is our function right here. This is our famous parent function right here. Is it 1 to 1? Okay, and why is this important? Well, let's answer it here. So you got to remember what 1 to 1 means. So, what does 1 to 1 mean? Well, 1 to 1 means that the function has its inverse. Okay, in order to be 1 to 1, the function must be a function and pass the horizontal line test. Okay, so let's put that down. So 1 to 1, 1 to 1 means that it must pass. Function must. When I say must, function must pass. Function must pass the horizontal line test. All right. So that the input of that function gives you only one output, not multiple outputs like we're getting right here. Okay, we're getting like an infinite number of outputs from the inverse function, which is a problem, as I was saying earlier. Okay, so does it pass the horizontal line test? Well, guess what? The obvious answer is no, because I drew a horizontal line right here. So look in red, I got a horizontal line, okay, and it intersected, let me see, 1, 2, 3, 4, 5 times here. But remember, this sine curve is infinite. It never stops, right? It keeps on oscillating up and down. Bounces from -1 to 1 forever, right? And so the horizontal line intersects an infinite number of points. So it really has an infinite number of solutions here. And that's a problem, because when we take an inverse sine of a ratio, we want only one answer back. Okay, so I'm going to say, is it 1 to 1? And the answer is no, because it fails the horizontal line test. So let's respond that way first. So no, it fails the horizontal line test. Okay, HLT for short. Okay, and so this means right here, this implies, could draw an arrow over here, okay, that the inverse is not a function right now, unless we restrict it. So this implies, at this point right here, implies that the function, this sine function, let me be more specific here. So sine theta, all right, does not have, if I can spell here, come on. So it does not, all right, have an inverse unless we do something about it, okay? This is not a good situation, okay? Not good. All right? We need to do something so that the function does have an inverse, because guess what? We need to take the inverse of We need to use the sine inverse sometimes to solve equations. And sometimes we need to take the cosine inverse or the inverse cosine or the inverse tangent or the inverse of any one of the six trig functions. Okay, so how do we do this? Well, number 5 gives us an idea. It says restrict the domain. All right, so this is an important thing we're going to do here. We're going to restrict the domain here, the graph, above to give the longest possible interval with no repeated outputs, okay? So that it passes the horizontal line test. Okay, so how can we do that? So let's look in the graph right here. What portion of the graph, okay, and it says the longest possible interval, not the shortest, but the longest. So what portion of the graph can we take so that it passes the horizontal line test? So if we take a look at the one period of sine, I'm just going to highlight some areas here from 0 to 2 pi. This is what the graph looks like when we graph one period of sine. Okay, it doesn't pass the horizontal line test here. So notice that I just drew a horizontal line and intersected twice. So we can't choose the interval from 0 to 2 pi because it doesn't pass the horizontal line test many different times. All right, so that was a bad choice. So I'm going to delete all this stuff here. Okay, so it can't go from 0 to 2 pi. Can't go from 0 to pi. 0 to pi wouldn't work either because it fails the horizontal line test there. So that's no good. So delete that. How about from 0 to pi? Pi to 2 pi. No, that doesn't pass the horizontal line test either. So scratch that. All right, so what interval can we take so that it passes the horizontal line test? Well, let me see. How about from 0 to pi halves? How about this one right here? That would work, okay? That would work. You know, half a pi is right here. That would work, but it doesn't say the shortest possible. It says the longest possible interval. Longest, not shortest. So is there another part of the sine curve that we could look at so that it passes the horizontal line test? And the answer is, okay. Answer is, oh, drum roll. Okay. How about from negative pi halves to pi halves? Okay, so right here, negative pi halves to pi halves in that little interval. So from the minimum to the maximum. All right. Okay, so at the minimum to the maximum right here. And if you draw a horizontal line anywhere there, it's going to intersect at only one point. Okay, so what we want to do is restrict it here. Okay, so let's draw some vertical lines. We want to restrict it from negative pi halves. Okay, restrict the function so it does have the inverse. And so let's respond to number 5 here. So our restriction now, okay, so restrict the domain. Come on, let me grab a color here. So, oops, sorry guys. So restrict the domain, all right, from negative pi halves to pi halves, okay, so that the sine inverse has so that sine inverse is a function. Okay, so that the inverse exists. Okay, so I'm going to say, and let's go to red now. Okay, so the sine function right now, okay, is 1 to 1. So now I'm going to be specific. Is 1 to 1. Okay, which means it passes the horizontal line test. Okay, on the interval from negative pi halves to pi halves. Okay. So now sine inverse exists, and now we can take the inverse sine of an angle. Okay, so what am I saying here? I'm saying that sine inverse right here, whatever you take, it has to be between, okay, negative pi halves and pi halves. So the other way you can write it is this way right here. So negative pi halves is less than or equal to, all right, the inverse sine function, the inverse sine of x right here, and it's got to be between negative pi halves and pi halves. It's going to return an angle between negative pi halves and pi halves, which, if you think about it, has to give you an angle in either quadrants 1 or 4. So let me show you why. So let's draw a little line diagram here. So if you plot 0 and you plot pi halves here, and then you plot negative pi halves over off to the left right here, between 0 and pi halves is obviously quadrant 1, and between 0 and negative pi halves and 0, well, that's a clockwise rotation, and that's quadrant 4. So when you take the inverse sine of a ratio, it gives you an angle either in quadrant 1 or 4, no other place. Okay? All right. So that's how we restrict sine. Now let's restrict cosine, and then we'll go to tangent, because we got to deal with all three functions here, because this lesson is leading into solving equations. And when you solve equations, trig equations, it always involves an inverse, okay, when you find the angle, as you're going to find out in the next lesson. So here we go, number 6. Can you use the same interval to restrict domain of cosine theta? If not, what would the interval be? Well, let's draw in the same interval here. So from negative pi halves, let's plot here so we can see things. So here's negative pi halves, right there, and then pi halves is over here. You know, half a pi is pi halves right here. And if you highlight the part of the function that is between negative pi halves and pi halves, okay, you can see that if you draw a horizontal line, it intersects it twice. All right, no good. All right, so that is definitely not, all right, not a good interval to choose. So what interval would you choose so that it passes the horizontal line test and cosine has an inverse? Okay, well, you could take the interval from 0 to pi, okay, and restrict it that way. So get out your red pen here, and let's draw dotted lines here for the restriction. So we're going to restrict cosine, all right, in this interval right here. There's your restriction. Okay, so from 0 to pi. And notice it passes the horizontal line test. If you draw horizontal lines, it only intersects once. All right, so the answer to our question here, if we were going to, number 6, can you use the same interval? You say no. Okay, because it doesn't pass the horizontal line test. Okay, and then if not, what would the interval would we use? What interval would we use? Well, I just said 0 to 2 pi. Okay, 0 to pi. So on this one here, we need to use, let's put this actually in red. Okay, we need to use 0 to pi as our interval to restrict cosine. So what we want to do is, let's write this over here. So the restriction, so cosine inverse would be between 0 to pi, excuse me. So 0 less than or equal to cosine inverse of the ratio here, and that's got to be between 0 and pi. Okay, so we can only take the inverse function. So when we take the inverse of this ratio, it's going to return an angle between 0 and pi, which means if you draw a little number diagram here, okay, so here's 0, and here's pi halves, and then here's pi. Okay, as you guys know, between 0 and pi halves is quadrant 1, and then between pi halves and pi is quadrant 2. So it's going to either give you, when you take the inverse cosine of some ratio, it's either going to give you an angle in quadrant 1 or 2. And you're not going to get an infinite number of angles, as you're going to find out, because that wouldn't be good. Okay, having an infinite number of solutions to a problem, a real context problem that requires only one solution, okay, that wouldn't be a good situation. So number 7, use your interval from number 6 to evaluate the inverse cosine of negative root 2 over 2. Okay, so cosine's negative in quadrants 2 and 3. Okay, so as I said before, the inverse cosine function is restricted to either 1 or 2, and so in this case, it's got to be a quadrant 2 angle. Okay, and they're asking you here, when you take a inverse cosine of a ratio, what they're asking you is the cosine of what angle theta gives you a ratio of negative root 2 over 2. So what would that theta be? This is equal to theta. What would that be? This is an angle. So the inverse function takes you from the ratio back to the angle that it came from. All right, and so you got to answer that question. So what would it be? Well, it's got to be a quadrant 2 angle, so theta must be in quadrant 2 because the ratio is negative, okay? So what would it be? Well, let's see here. Let's look at the unit circle here. Let's go over here to the unit circle just for funsies right here. So notice the cosine values. Look at the x coordinates here, and this quadrant 2. So quadrant 1, quadrant 2, quadrant 3, as you guys know, quadrant 4. We have to look in quadrant 2, and there's only one ratio that has a value of negative root 2 over 2, and guess what? That's 3 pi fourths. Okay, it's not, it can't be down here. Okay, it can't be 5 pi fourths because that's quadrant 3. And remember, it's restricted. You're either going to get an angle in quadrant 1 or 2, not quadrant 3. So the answer of the angle has got to be 3 pi fourths. Okay, so where's my answer? Okay, so theta must be, or the, actually, yeah. So let me write it like this. So the inverse cosine or arcsine of negative rad 2 over 2, it's an angle. Okay, remember this is an angle now, so you have to understand that, is equal to 3 pi fourths in quadrant 2 because it's negative. It's not in quadrant 1. Okay, and we got 1 back, and that's important because, like I said, we have to, when we're solving equations here, we don't want an infinite number of answers, okay, when we solve real context problems. Here, the inverse function should return one and only one answer, so we have to restrict it. So whenever you take the inverse cosine of a ratio, it's got to return an angle in either quadrant 1 or 2, not anywhere else. So it's either one or the other, not both. Okay, one answer only. This is how many answers should you get? One only. Okay, on what interval is the tangent of x 1 to 1? Okay, where does it pass the horizontal line test? Well, first of all, if you zoom in here, if you just draw a horizontal line anywhere, okay, it intersects an infinite number of times. So we already got a problem. It's not 1 to 1. Okay, the tangent function is not to 1 to 1. You must restrict it. Okay, tangent x is not 1 to 1. Okay, because it fails a horizontal line test. Okay, that means we have to restrict the function. So restrict the function. So on what domain? So how so? What domain should we choose? Okay, oops. Sorry guys, didn't mean to. So what? Okay, what should the restriction be? Okay, so we know that the asymptotes on this function exist at negative pi halves. Okay, and pi halves, we already know that. Okay, that was from our first lesson here. So these are your vertical asymptotes for the function at negative pi halves and pi halves. And if you take a look at just that period, okay, just look at one period only. Remember, this period of tangent is pi. All right, the distance between negative pi halves and pi halves is pi. If you look at one period only, it does pass the horizontal line test. All right, so we need to restrict the tangent function from negative pi to pi halves. Okay, so my answer is, okay, from negative pi halves to pi halves. So the inverse function is between these two values. So the way you conceptualize it and write it is that the inverse tangent now, or arctangent, of some ratio x, okay, so x is now a ratio, not an angle, okay, it returns an angle, but it doesn't, you don't take the inverse tangent of an angle, is got to be between negative pi halves and positive pi halves. So what does that mean? So if you draw a little number line like I did before, and let's see, here's 0, over here on the left is negative pi halves, on the right is positive pi halves. As I said earlier with let me see, the sine function. So yeah, look up there. So on the sine function here, we went from negative pi halves to pi halves. That's quadrants 1 and 4. Same thing down here. 0 to pi halves is quadrant 1. Negative pi halves is 0. That's quadrant 4. So when you take the inverse tangent of an angle, it either gives you an angle in quadrant 1 or 4, but not both. Okay? So there we go. All right. So now let's start applying here. Let's take some angles and let's go for it and apply it. Okay, but let's do some learning targets here first. Okay, so basically here we got 3 functions. So let's just talk about your inverse functions here. So first one here. So let's consider our first function, just summarize everything in one little spot here. So let's say you got this inverse function, f of x equals the inverse sine of x, or you can write it as, look at this, arc sine of x here. Same thing. This is called an inverse. Okay. The domain on that is you can only take a number from negative 1 to 1. Okay, so the domain of this function is from negative 1 to 1. So you can only take the inverse sine of some number between negative 1 and 1. That's your input. Okay, the output, which is called your range or output here. Okay, what is that? Well, let's go back up here and let's just refresh our memory right here. So we had to restrict the sine function from negative pi to pi, right? Excuse me, from negative pi halves to positive pi halves. And where did I write this down? Okay, so yeah, right here. So the inverse function is restricted. It's going to give you an angle in either quadrants 1 or 4. Okay, so here we go. So the output here is between negative pi halves, okay, and positive pi halves. Now the way you can write that really succinctly, like really easily here, is just use closed interval notation. But you really have to understand something here. These angles in here, if you do a little sign or a little number line diagram here. Again, I said this earlier, but I say it again. From 0 to pi halves is quadrant 1, and from negative pi halves to 0 is quadrant 4. So if it returns an angle between negative pi halves and pi halves, you're looking for an angle in quadrants 1 or 4. Okay? All right. Next one, the cosine function. So what does that guy look like? So let's say we're given the inverse cosine function, which can be written this way, or it could be written as arc cosine here of x, either one. The domain for that is the same as sine. You can only take the inverse cosine of some number between negative 1 and 1. Okay? And it gives you back an angle, which is in the range, okay, between 0 and pi. Okay, so I said earlier that 0 is less than or equal to the inverse cosine of x, which is less than or equal to pi, but the easy way to write that is from 0 to pi. And these are 2 different quadrants, so if you plot this here, if this is 0, and this is pi halves, and this is pi, right? This is quadrant 1, and this is quadrant 2. So the inverse cosine function will give you an angle in either quadrant 1 or 2, but not both. It depends on where it's positive or negative. If it's positive, it'll give you quadrant 1. If it's negative, you'll be in quadrant 2. So just keep that in mind. Okay, and the last one here, okay, if we have the inverse tangent function, which you can write it like this, the inverse tangent of x, or you can write it as arctangent of x, either way. Okay, its domain is all reals. Okay, because remember that tangent function went infinitely up and down. So now you could take any real number, okay, so from negative infinity to positive infinity, but it's going to send an angle back, which is in the range between negative pi halves and pi halves. So okay, just my train of thinking here. Okay, so, oh yeah, I know what I was going to say. So from negative pi halves, all right, so it's got to be between these two numbers here, and pi halves. So just like the first one, just like the sine function, again, if you label this right here, and you have to understand that these angles that you're, oh, you know, I put in less than or equal to, it should be just strictly less than. So I'm going to change this right here, strictly less than. Sorry, strictly less than, strictly less than. Okay, and then here we go. This is quadrant 1 over here. From 0 to pi halves is quadrant 1, and then negative pi halves to 0, that's quadrant 4. So when you take the inverse sine of some real number here, all right, it's going to give you an angle in either quadrant 4, either one or the other, but not both. So remember that. And the range, just a way you can write that succinctly or just nice and neat, is from negative pi halves, open this time, all right, to positive pi halves, open interval. Okay? And now I'm going to do the rest with you guys in class. Hopefully this helped you out. This is the initial lesson that we did in class, and of course you got to apply it, right? Which means you got to practice. All right, do your check for understanding, check it with my notes, and also do your homework. And if this doesn't make sense, well, then come in for some tutoring and work on it, okay? Give me your best, and I'll see you later. It's Aynesworth. Take care. Bye-bye.